Welcome to Walkabout the Galaxy, the charmless astronomy podcast, where the science is universal, the opinions are personal, and the trivia is topical. We are strange up and top the astroquarks, also known as Josh Caldwell,
Hannah Sargent,
and Jim Cooney.
Coming to you from the Walkabout studio at the University of Central Florida. Charm Quark got stuck in a particle accelerator.
Oh, no. That sounds very bad for your health.
We'll try to get her out of there for the next episode. Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram. Our YouTube videos now actually appear when we publish our podcast.
Nice.
So you can watch our looks of panicked confusion carefully masked by our oral skills. You can learn now learn about UpQuark at walkaboutthegalaxy.com, where you can also see how to order a Walkabout shirt and support STEM education at the same time, and contact us at wtg@ucf.edu. Definitely do contact us that way if you order a shirt so we can get it to you as soon as possible. Our Stumper today, we've got a little bit of a series going. We've been playing around with godlike tinkering of the Earth's orbit and spin parameters. So I think we've previously asked you how long you would like the day to be if it didn't affect anything else, and we think we got some surprising answers on that one. At least they were surprising to me. And then the last was shape of the orbit. So today we're going to talk about the Earth's obliquity, jargon
Fancy word.
Which is the angle between the axis that the Earth spins on and the angle that it orbits the sun on. So the angle between the Earth's equatorial plane and its orbital plane.
So, like, how tilted does it spin?
How tilted does it spin? Why didn't I just say that? I don't know. That's why you're here, Hannah.
Yeah, I like to simplify all this word.
So the obliquity, we care about the obliquity because it's actually the reason we have seasons on Earth. The orbit is so circular for Earth that the little change in distance of the Earth from the sun as it goes around the sun doesn't really do anything as far as seasons go. But half the year, the North Pole of the Earth is tilted towards the sun. And 6 months later, it's tilted away from the sun. So you get much less direct sunlight hitting the northern hemisphere.
Yeah, almost everybody, when I ask my intro astronomy classes, they know it's associated, the seasons are associated with tilt. But they're totally convinced that it's because that brings it closer. Tilting it brings it closer. I mean, and it's reasonable until you understand something about the scales of things, right? I mean, making it a couple 100 kilometers closer by tilting closer is irrelevant because the sun is friggin' 150 million kilometers away, right?
Yeah, this is one of the values of like the scale solar system idea, because on that, the scale solar system we talk about usually is a 10 billion to 1 scale. The sun is a grapefruit. 15 meters away from that grapefruit is the ball of a ballpoint pen. That is the Earth.
Right.
Just think about that. You can tell that it really doesn't matter which side of that ball you are on in terms of how much energy you're getting from the sun.
Right.
So it is that tilt, and it's because of the directness
because of how
the sunlight hitting the surface. So if you could tinker with it, again, with magical powers so that I don't want you worrying about the rest of the ecosystem. We're going to assume that that's all fine. Just your personal preference. How would you like the seasons to be?
There's a right answer. Go, Hannah.
Oh, no, there is not. Come on. No. For this one, you can go first, and I will consider a response.
I decided that the only correct response is 0.
When you said there's a right answer, that's the only number you could be thinking of.
Yes. I 90. Or 90. Yeah. I was thinking 90s. But it's got to be 0. Symmetry is beautiful. And that's why all the most beautiful people, like 3 of us, we're symmetric.
I'm very splotchy today.
Oh, well, then you're not as beautiful as we are. But
temporary.
Straight up and down. Then every day is the same as every other day.
No seasons.
Seasons.
Spoken like somebody who's not a big fan of change, and I can.
That's right. I am not a fan. I freak out.
Relate to that. Yeah. You know, I would just get the same thing at the same fast food restaurant for every lunch and dinner, and just mix it up at breakfast.
Yeah. I'm with you.
No, I need variety. I really do need variety. So I don't think I would change it because I like seasons and I like I like.
And they're just right the way they are.
I like that there's that you can go to different places on the planet to get the kind of variety that you're comfortable with.
Okay, right. So you can go to Hawaii, for example, and have almost what Jim is describing,
Exactly.
because the climate there is beautifully beautiful and constant-ish.
Yeah.
And then if you want more seasonal things, then you can go to the UK.
Right.
And I like that. I like that there's options as opposed to constant everywhere all the time.
Yeah.
But then you get more extremes, which is interesting.
Right.
So
yeah. There's something to be said for the 90-degree obliquity.
Yeah, that's pretty.
Where then you would have some variety, Hannah. You would have some really interesting variety, and there would be a part of the year when England would just be sort of tropical.
Be melted and
It would be tropical. But of course there would also be a part of the year where it would be midnight for
and that does not feel
days and weeks
at all.
Right.
So,
yeah. Okay. Well, today we'll talk about a gigantic shock wave from colliding clusters of galaxies, a briny asteroid, and black holes quenching star formation. But first, this episode of Walkabout the Galaxy is brought to you by the Yarkovsky effect. Chemical rockets may be flashy and ion rockets may be fancy, but let the Yarkovsky effect get you back to basics and fly around the solar system on the power of photons. Thanks to thermal inertia and black-body radiation, the Yarkovsky effect can either boost or decay your orbit, depending on the direction of your rotation. As a bonus, you can explore slowing your rotation or increasing your obliquity to allow the seasonal Yarkovsky effect to spiral you in toward the sun. For your orbital maneuvers, try the Yarkovsky effect. Choose where your power comes from.
Choose where your power comes from.
Choose where your power comes from.
Is that a fuel?
Sort of. You'll never guess it because you probably never heard of it. But you can guess.
Could you sound any more like let down by that? You're never going to get it.
You're never going to get it. But you know, if you get close to it, you get 45 points.
Okay.
GM
and,
I don't know.
And something. What did you say? Something. Fuel. It's a solar company.
Yeah.
Solar
power.
Okay.
Yeah.
Yeah. Sunrun, which is puts residential solar panels up.
So choose to be better for the planet. And
Choose to get your power from the sun, for example. There was another Starlink launch. We're like not even really counting anymore.
it's like every week.
Yeah. So they've launched over 2,200, as we've discussed before. Several of those have come down, and some are not functional, but probably 90% of them are up and functioning at the moment. So on the order of 2,000. They're still not even halfway to their initial planned deployment of 4,400.
Poor astronomers.
Yeah.
Yeah.
Lament the poor astronomer.
Yeah.
That launch, which was yesterday from nearby, was the 11th launch of that particular Falcon 9 booster. So the reusability thing is really a thing.
How much refurbishment goes in per...
I don't know.
Okay.
Right? So I don't know.
Yeah.
These things are, to my simplified understanding, you got a big tube and some gas tanks in there, right? So an oxygen tank and a kerosene tank. I think they're Raptor engines, I believe, these are Merlin engines, I believe, are kerosene fueled. So they have a kerosene tank and a liquid oxygen tank. Then they have 9 of these engines. And those are really probably where a lot of the financial value of these boosters lies. So I don't know, but...
That's an interesting point, though, because like these days, for a lot of things, it's easier to replace them. It's cheaper to replace them than it is to like fix them or clean them, right? Like computers and things like that.
Yeah, if your TV breaks, you're just like, chuck it
because it's cheaper. It's cheaper to get a new one than fix it. So I wonder how much you're saving by cleaning these rockets rather than.
I'm pretty sure they're motivated by financial.
Right. No, I'm sure that it is. I just wonder. I wonder how close it actually. And like obviously that was like the whole point of SpaceX and all this stuff to begin with is make spaceflight cheaper by reusing rockets and things like that. But I wonder how expensive it actually is to refurbish one of these things and get ready for the next flight.
And I wonder how much they learned from the shuttle era and seeing what can be reused and what can't. And,
right. Yeah. So the engines themselves, certainly, you turn them on and turn them off. Even in a single flight, they're turning these things off and on, so they're throttleable. And, they're not one of these things like a bottle rocket where it's like you light it, or like the solid rocket motors. You light it, and, that's it. Although, to be fair, the solid rocket motor casings for shuttle were reusable. So I don't know, but they have obviously brought the cost down. I mean, just talking about the number of these Starlink satellites that they're putting up, they've managed, at least they have a business plan where this is in principle making financial sense. However, it hasn't brought it down to the point where an orbital launch is just like a couple $1 million. So it's always been on the order of $100 million.
Wow.
And it's still many tens of millions. So the reusability has not like, oh, we reused this first stage 10 times. It has not made it 10 times cheaper.
Right.
So first there's the upper stage. There's all of the services, all the work and that has to go into the launch. It's beyond just the hardware itself.
I wonder as well how much the automation that they've managed to bring to this is bringing down costs as well. Even just having the drone barge and everything else, all of these things kind of cumulatively will be saving money. But and it's just really cool. I love the barge.
Yeah, the barge is cool, but it's more cool when they come back here.
Yeah,
because we can actually see them landing here, which is also super cool. So that was interesting. I wanted to just mention briefly on the nerd news topic, super short, this show called Severance. Did we talk about
Severance?
That?
I've never heard of it.
Let's just assume I haven't seen the Sci-fi show.
Yeah, this is a show where there's a technology that a company, you can volunteer to have an operation that you only remember work when you're at work, and you forget it as soon as you walk out of the building, and you only you don't, and also when you're at work you don't remember home. So it cuts you into two people, basically. One person who is the work you. So it's talking about work-life balance.
But then how do you leave if you don't remember home?
Well, as soon as you walk out the door, you change into that other person, and you're just like, oh, I'm this person again, and you go home. But it's very creepy because what if you go back to work voluntarily, having no idea what horrible things you might be doing there?
Right. Yeah, you're like slaughtering children or something like that.
What kind of work does that involve?
I know, right? But and you always cheerfully go back in there because the outside you doesn't know what it is you're walking into.
Yeah, that sounds like an episode of Black Mirror.
Yeah. Oh, don't do that because they seem to come true. So let's.
Yeah. Well, in a little bit we'll have special Top Quark trivia, but we'll work our way out in the cosmos today. And we have a solar system story.
We do. We're at the asteroid belt, so pretty close to home. And you may remember or have heard of the Dawn spacecraft. So this was a mission that went to go visit Ceres, the dwarf planet, and Vesta, I believe.
Yes.
So that mission is now, it's ended, but there's still kind of processing some of the results from that and publishing the results from that mission. And there's a recent publication that's come out looking at some salty brines in this large crater.
What's a brine?
A brine is a salty, very salt-rich liquid.
A salt-rich liquid.
So early on there were these famous pictures of these bright white spots in that crater. So is this further analysis of those spots?
This is a different crater.
Okay.
And apparently within the salts, they have this organic rich material, and apparently the salts are actually different to the other craters. on Ceres. So the composition is slightly different, which is...
Different salts on other craters?
Yes.
Okay.
Which is interesting. And so just for kind of context for this, they've been looking at, so this crater, let's see, Avara Basin. And this is a very, very large impact. And we know this because when you have these large impacts that are so big that they create this central peak.
Right.
So, and in that central peak, it's got this material that has been dug up from much deeper within the I guess, interior
of the asteroid. Yeah. So this is Vesta, you said, or
this
Ceres?
Is Ceres.
Ceres, which is the largest asteroid, and it's about 1,000 kilometers diameter, 900 and something.
Ninth planet?
940 kilometers in diameter. Protoplanet, dwarf planet.
Ninth planet.
Ninth planet.
Totally a planet. 100% a planet.
Are we going to get...
Don't get me started. Anyway,
okay, yeah.
Okay. It's round. It's a sphere.
Yep.
And it's but smaller than the moon. And how big is this crater? About 50 or...
let's have a look. 170 kilometer wide.
Oh, okay.
Big boy.
So it's a significant fraction of the size of the object. And if we're talking about crater classifications, tiny craters on these, we don't get tiny craters on the Earth because anything that would make a tiny crater burns up in the atmosphere.
Right.
But on the moon or an asteroid where there's no atmosphere, you do get tiny craters. And they're these beautiful bowl shapes, just like a cereal bowl or something like that. And I'm going somewhere with a cereal.
Serious bowl, yeah.
And they're just these nice, look like you took a ball and just sort of pushed it into the surface and pulled it out, and you made this nice spherical indentation. But when they get bigger, the craters start getting more complicated, and it's partly because you're putting huge amount of energy when these impactors come in, and it liquefies the area that it's hitting.
Yeah.
And so you have all sorts of flow and stuff, and then you get flat-bottomed craters because the material that's been liquefied sort of comes back. And the central peak, my cereal story is if you ever drop a Cheerio into your milk.
Oh, and you get that immediate splash in the middle.
Yeah, that's the central peak, right? It's just that if it's a big scale on an asteroid, that splash coming up freezes.
Yeah, it solidifies, right?
Yeah.
Back into a mountain.
And it captures this kind of interior mountain in the middle of these giant basins. And what's particularly interesting is that they found that I think they've tried to do some aging on this using crater counting, and found that there are areas within the crater that are much younger than the crater itself, as in there have been processes that have been continuing on long after the basin had cooled and everything else. So it's suggesting that there is some geological processes that have been continuing on, that these brines have been flowing. So
there's some evidence that something has covered up older craters inside in some areas and not others, or something like that.
Yeah. And this is just, and it's kind of, it's particularly interesting in terms of astrobiology because you have organic material, you have flowing maybe these brines, these liquids. So is there potential for there to be conditions for
Could it be
life?
Like a giant space worm?
A giant space...
big enough to eat the Millennium Falcon.
So we are talking Star Wars.
Yes.
Okay. I don't think there'd be enough salty brines to support giant worms.
Well, it would occasionally eat a passing spaceship.
But yeah, so I thought
what about sea monkeys? Sea monkeys... If you remember,
Hannah is really trying to.
I do remember.
She wants to talk science, but we're being idiots.
Come on, sea monkeys.
Sea monkeys. I think Hannah said that she had sea monkeys when she was a kid. Josh, did you have sea monkeys? They're brine shrimp, so they must be on Ceres.
I would love to find some sea monkeys because my brother killed my sea monkeys when I was younger, so I'm pretty upset.
I never got the sea monkeys.
You never got sea monkeys?
No.
Oh, man.
They gave me the creeps, all those ads for sea monkeys.
They play baseball and things like that.
We did not get those ads.
So that's interesting. So it's geologically active at some level.
At some level.
Okay.
But yeah, so
when you talk about organic material, we're talking about simple hydrogen carbon molecules.
What are they called?
Like
the chin-ups? Do you remember that?
Chons I know about.
the carbon, hydrogen, nitrogen, oxygen, phosphorus, maybe? I forget. But anyway, yes. So these, it just says organic material. Okay. And I thought it was a cool story, but then I found that it's they've already, as you say, they've already found these salts in other craters on Ceres. I think the only difference is perhaps that they've got some slightly different salts that they're
so the recent geological activity was news to me, but the thing that's surprising about all that, well, there a lot of things are surprising about it, I guess, but we've talked about geological activity on small objects before, like Enceladus and Europa, these moons with oceans underneath, and they've got stuff coming out on the surface. But there, at least, we have some idea about a heating mechanism that can provide the energy to keep that going. Ceres is just there in the asteroid belt, which, Star Wars aside, is really a very, very, very empty place. Mm-hmm. It's like most of space. You're not going to run into anything else. So, what would be going on? Is there radioactive materials that are perhaps hypothesized to be driving this geological activity, or is that...
I can't tell from the information that they're giving here. It just says that more questions are being asked. It's opening up different ideas about, for example, where are these salts coming from? Is it that salty brine has... the salty brine is coming from deeper within the surface, or it's salts that are coming up and then turning into brines just below the surface. So there's still many questions that are being asked, but it's just, I think Ceres is more and more interesting, and is more things are happening on Ceres than we initially would have thought.
All right.
That seems like a thing that we see very often. It's the same with like Pluto and New Horizons, when they're like, I thought it should have been pretty much a dead thing, and it turned out to be a very geologically active, interesting place.
Right.
What gives?
Yeah. The universe is an interesting place.
It is. Turns out that's awesome.
Somebody should do a podcast about it.
That would be a winner.
All right, Jim, you get to stump me and Hannah today.
All right. So I, this past weekend, finally watched the first episode of the Book of Boba Fett.
Yes.
I think that's what it's called. The
Chapter
new
1 of the Book of Boba Fett.
Right.
Yes.
The new Boba Fett series. That it's very stylistically similar, and it happens at the same time as the Mandalorian. Mm-hmm. I actually very much enjoyed the first episode. I don't know about you guys, if you've seen it or not.
I've seen it.
Did you enjoy the first episode? Don't say anything more about it, because I only saw the first one.
I honestly don't remember how I felt about the first episode.
Yeah, I enjoyed it. So the trivia today, there are multiple parts, of course. The first couple parts, though, are Boba Fettnol.
Okay.
And that's going to make it. I know that's going to make it difficult for our good friend Hannah, because she doesn't really watch these things with the religious intensity. Yeah. But the follow-up part that I'll ask once we come back to it will be more biological, and maybe you can.
I will do my best.
So your first question is very simple and quick. Boba Fett.
Yes.
Where did he first appear? When was his first appearance in the Star Wars universe?
Okay.
And then as a follow-up, not the only follow-ups, the better ones will be later, is who did George Lucas base his character on?
Boba Fett's character was based
on a character from a different
fictional
universe.
Okay.
And so that one's tough because but you should be able. There aren't all that many choices for the first one, and I'm not even going to give you them.
Okay.
So
no, I know the answer to the first one. I'm pretty sure.
Oh, that's going to be nice.
Because I don't really watch a huge amount of Star Wars, but I love behind the scenes. So I've watched many a behind the scenes documentary where this kind of stuff has been mentioned.
Yes.
And so
you might just know it,
I feel like it's in there somewhere. I just need to dig it out.
All right. Well, you got like 15 minutes. All right. Mull it over.
Okay.
All right.
Our next topic is about massive black holes. What else? Right? We love talking about massive black holes.
Yeah. They're freaking awesome.
This in connection to star formation rates in galaxies, which is something that has come up, I think, a few times in recent episodes, so that galaxies sort of go through a life cycle. We talk about individual stars' life cycles, and we've talked about this main sequence, which refers to a particular sort of stellar map, or I don't know how to describe the Hertzsprung-Russell diagram in a nice analogy or metaphor for the Hertzsprung-Russell diagram, but it's a way of sort of showing. It's kind of like a demographic pyramid or something of sorts for stars. If you think about a population diagram for people, and when stars are in the prime of their life, they have a certain sort of color, temperature, property, and then they evolve a certain way. Galaxies do a similar thing. The Milky Way galaxy, when galaxies first form, there's a lot more star formation going on, and big stars burn up their fuel quickly and explode in one fashion or another and put most of their material back out into the interstellar medium, which can then form the next generation star and so forth. But each time you do that, you form some smaller stars. And those smaller stars just last. They just last and last and last.
Yeah, it's like the lifespan of a low-mass star is longer than the current age of the universe. Yeah,
right. Wow. So they just keep going and going and going.
Yeah.
And that means they're locking up that material, the raw resources that you need to make the next generation of stars. So the rate of star formation declines in galaxies over time. So one element of that just sort of occurs naturally is you start just locking up more and more material inside things like small stars and then white dwarfs and whatnot. So there's not much material there. But there's still lots of gas and dust that can trigger star formation, but we see something called quenching of star formation in galaxies. And there's a kind of a galaxy demographic plot called the galaxy color magnitude diagram. It needs to come up with a...
Yeah, we need a better name for it than that.
For stars, we have the Hertzsprung-Russell doesn't roll off the tongue, but that gets abbreviated to HR.
So this
the HR diagram.
GCMD?
The GCMD.
Yeah.
Somehow that sounds like maybe something to do with cell phones.
Yeah, Caldwell-Sargent-Cooney diagram, yeah.
Okay.
Oh, there we go, named.
We have absolutely nothing to do with
Doesn't matter.
Galaxy research, but why not? That has color on one axis and temperature, luminosity rather, on the other axis. And galaxies clump into, I thought this was sort of charming, into two main groups, the blue cloud and the red sequence, which are separated by the sparsely populated green valley.
Oh,
I like
beautiful
that.
Green Valley.
Let's go there.
I'm happy you like it because it turns out the Milky Way is in the Green Valley.
Of course it is.
Oh, nice.
The Milky Way and the Andromeda Galaxy are both in the Green Valley.
So does that mean that we are around a pretty bog standard sun in a very bog standard galaxy?
That means we're...
What did you say?
Oh, what? Is that not a thing?
Bog
standard? Like average.
B-O-G?
Average, like pretty middle of the road.
But please explain the etymology.
I have no idea. I don't, bog
How is
standard.
it spelled?
Bog, B-O-G.
B-O-G. Okay.
Okay, so that's
I wasn't
new.
sure if you were saying bog or bug.
Oh, okay.
Bog, like a swampy bog.
Yeah, swampy bog.
Yeah, I guess.
All right, fair enough.
There you go. There's a new phrase for the day.
Great.
Yep.
Okay. No, it actually means, so in the blue cloud, oh gosh, I'm going to get this backwards, but one of them is mostly elliptical galaxies that are cranking out stars at a pretty hefty pace still, and the other is mostly spiral galaxies that are much less active in star formation.
It's going to be the other way around.
We're heading into that, so we're in the middle. The green is in between the blue cloud and the red sequence.
Does that mean that we're slowing
Generally,
down?
elliptical galaxies do not have much gas and dust, and spiral galaxies
Did I get
do.
that backwards?
Yeah.
Sorry.
So
But it's okay.
are all galaxies progressing from high formation to slow formation?
Yes,
Okay.
generally. So I said that backwards. It's the ellipticals that have much lower star formation?
Correct.
Cheapers. Okay. Yeah. Anyway, we're heading towards the lower formation rate. But we're not about to become an elliptical galaxy.
No, generally, I mean, elliptical galaxies... I mean, generally, when galaxies first form, spiral is kind of the preferred way to do it. And then as you collide a bunch of galaxies together, then you end up with these elliptical galaxies. So elliptical galaxies, like often at the centers of galaxy clusters, there's one big giant elliptical galaxy that is kind of the result of. And yeah, they tend to be filled with older stars and less gas and dust, and so.
Okay. Well, in any event,
they're redder.
Okay. So there is a quenching that occurs in the central regions of massive galaxies, and there's been some debate about what's the cause of that quenching. And it seems that supermassive black holes may be the culprit.
Oh, no.
So in particular, what the research here did was they used a machine learning classification and found that the presence of supermassive black holes was the most predictive parameter in determining whether or not star formation is quenched in a galaxy. So they did various sorts of simulations with all the different parameters going on, and the supermassive black hole was sort of your predictive parameter for shutting off star formation. So why does that happen? I talked earlier about locking up fuel inside low-mass stars or stellar remnants or whatever. But to form stars, you need raw material, so you need gas. And then you need that gas to be
cold.
Could have gone one of two ways there.
You need it to be cold because if it's hot, that high thermal energy is greater than the gravitational binding energy, and it doesn't want to fall in on itself. But if it's cold...
Yeah, hot things have more pressure, right? I mean, if you heat up a balloon, it wants to expand. It doesn't want to collapse.
Right, yeah. So, and there's fun experiments. Take a balloon, an inflated balloon, dip it in liquid nitrogen.
And it collapses. So we want cold, dense...
Cold gas, so then it collapses in on itself and can make stars, which then gets hot. Right.
It gets hot at some point. There we go.
It definitely gets hot as it's falling in. So you need that raw material, you need the low temperatures. So explanations for star quenching basically boiled down to you get rid of the raw material, so by blowing the gas out some way, or you heat the gas up. And basically, this research is sort of pointing to a fairly simple explanation that supermassive black hole, the inflow into that fuels heating mechanisms that heat up the central regions of the galaxy and prevent that material from being able to undergo star formation.
So the gases are still there, but they just can't...
Right.
Not in optimum star forming conditions.
Correct.
Okay.
Yes. So this is not referring to quenching of star formation everywhere throughout a galaxy, out in spiral arms or something like that. So supermassive black hole in the Milky Way galaxy isn't doing anything to heat up gas in our local neighborhood or anything like that.
Right. Yeah. Right. But generally, in a spiral galaxy, the density of stuff is going to be higher towards the middle, and so you would generally have a lot of star formation towards the center if you could have cold gas. Yeah. But I guess it's hard to get that.
The title of the paper by Petrowska et al. Is on the quenching of star formation in observed and simulated central galaxies. Evidence for the role of integrated active galactic nuclei feedback in AGN. Active galactic nuclei is just another name for supermassive black hole.
Yeah.
So, black holes.
Black holes, just playing all kinds of roles in the universe that you don't think to. Yeah, they should just be sitting there doing nothing, but they're doing things.
Right. Okay. Speaking of galaxies.
Oh, yeah. This one's fairly short but fun. The biggest structures in the universe. You know me, I like the large scale structure of the universe and the very biggest things. The biggest gravitationally bound things in the universe are clusters of galaxies. So not individual galaxies, but big clusters of them.
Super clusters, or how
super clusters are not really gravitationally bound, right? So you could call it a structure, I guess, but not a bound structure. So the clusters, and so the collision between clusters of galaxies is like the most significant events in the universe that there are, because galaxies collide, or when clusters of galaxies collide, it's like the two biggest things there are or the biggest things there are in the universe colliding together. And because of things like what we talked about in the last thing, where supermassive black holes can spit material out from their galaxies into the intergalactic space. Turns out that in a cluster of galaxies, there's more mass in between the galaxies than there are in the physical galaxies themselves. Oh yeah, there's a huge amount of gas.
I share your surprise.
Yeah,
I know it is surprising. You don't see that, right? Because it's typically of course again the space in a cluster is huge, and the gas is spread out over all that area.
Ordinary matter or dark matter?
Well, there's both for sure. In a galaxy and outside of a galaxy, there's going to be more dark matter than regular matter. Right. But even if you're just talking about baryonic normal matter, there's more of it in between the galaxies than there is in the galaxies.
So this is because they are just so far apart that there is more space filled with
stuff.
Space filled with very, very, very diffuse stuff. But if you have enough space filled with diffuse stuff and add it up, that's a lot of stuff.
Talk about empty. Intergalactic space.
Yeah, it's hard to get emptier than that.
Pretty damn empty.
It's pretty damn empty. But you add it all up, it's a crap ton of stuff. And if you collide, crap ton, scientific description. But and when you collide two of these big giant clusters of galaxies, even though the gas in between the galaxies is super, super, super diffuse, there's still a shockwave produced by the collision between these things.
I do not understand that. I will just say that bluntly and plainly.
That's fair.
My conception of the generation of a shockwave involves physical collisions of things. So is this actually generated by the physical collisions of atoms?
Not necessarily, right? Because
atoms from the other cluster?
Yes and no. Largely no, but it's these clusters have very complicated, interesting magnetic fields, and when you smash one into the other, you take the electrons in the one and accelerate them using the magnetic field, the combined magnetic fields of the two, and this ends up. So it's not really one atom hitting another or one electron hitting the other electron.
Okay, well, good. I mean,
that's hard to take.
To wrap my head around.
Yeah. But so then you produce, when you collide these things, you produce these kind of shock waves that are, in some sense, similar to shock waves. I mean, shock waves are awesome. So you see videos of like bombs going off. I mean, you hate to see a bomb going off, but the shockwave part.
That volcano, which also was.
Oh yeah. That volcano. The amazing video.
Let's talk about Deep Impact, where there was a simulated shockwave from a comet.
I love simulated shockwaves from comets. It's way better than a real shockwave from a comet hitting Earth.
It's not hurting anybody.
No, I know.
In fact, it gives me a small royalty.
There you go. Yeah, shockwave. I mean, when bombs do go off, or like if a nuclear bomb goes off, a shockwave is a significant part of the devastating effect of that. I mean, there's the original fireball, but that doesn't really have that huge an extent. But the shockwave, you heat the surrounding atmosphere really quick, and that pushes out the atmosphere past that, and that pushes out the atmosphere past that, and so forth. And so it goes out.
And it's a shock because that pushing out is faster than the sound speed.
Right, faster than the speed of sound, so the air can't move out of the way, kind of.
So just outside it doesn't know that anything has happened inside until it gets hit.
Right. And so you get this big buildup of pressure right at the outside edge of the shockwave, and as it goes out, it crushes things and does all kinds of terror. This is what's happening as these electrons in the interstellar gases are accelerated to near the speed of light by intergalactic. Did I say interstellar? I meant this is bigger than that, man.
It's hard to wrap. Yeah.
It's harder. I know it is. They're accelerated near the speed of light by these magnetic fields, and so you get this tremendous shot. And of course, when you take electrons and accelerate them, you get light. Right, when you accelerate charges. And so we're seeing this shockwave in kind of radio light, which is the kind of light that's given off by these accelerating electrons. And we've seen the shockwave in a nearby, I say nearby, ish cluster.
A few billion light years or so.
Well, I think it's a few 100 million light years away, this thing.
That is nearby.
In these enormous shockwaves, they say something like 60 times the size of the Milky Way. That actually doesn't even impress me that much. That's big, but I could see it being.
Shania Twain.
Yeah, right. Oh my God, I really hate her in that song because I thought Being Smart was good, and she said she didn't care about that.
Wait a minute.
In the Shania Twain song.
What are you talking about? What song?
You're too old.
That don't impress me much.
Yeah.
Shania Twain.
Shania Twain. She's not impressed by being strong. She's not impressed by having a lot of cars. She's not impressed by being smart. I don't know. She's not easily impressed.
She doesn't sound like someone that we need to be impressing.
No, that's true.
Okay.
But back to the story of an impressive shockwave. I love the fact that it says these collisions release the largest amount of energy in a single event since the Big Bang, which as a statement,
that is a pretty cool statement.
Big.
Right.
Oh wow. Yeah.
Yeah. Just because it's not as flashy a thing as like a supernova or something like that, or one of these.
It's more spread out,
but it's so big, that the total amount of energy involved.
So this is entanglement. So the thing that's accelerating those electrons is the magnetic fields, and they're doing it because they're interacting So this is intergalactic magnetic field that are getting tangled up. Or, the magnetic field density is getting increased dramatically in some areas as these clusters are passing through each other.
Something, that is
wild.
It is wild stuff.
Yeah.
Pretty cool.
We should go back to something more banal like Boba Fett.
Boba Fett! All right. So question number 1.
Okay. I believe...
Where did Boba Fett first appear?
Do we have to count weird things between the movies?
You have to count anything.
Like Christmas specials and shit.
You have to count anything.
Sorry. Stuff like that. Because
beep that.
I'm okay, so I don't know about some of that stuff. I know that of the main Skywalker saga, the first one that he's in is The Empire Strikes Back.
Okay.
But I also have a feeling that there may have been some strange, weird thing like a Christmas special that came out in between.
Christmas special. A Star Wars Christmas special. That's ludicrous.
There definitely was a
Christmas special. It was ludicrous, though.
But also I have some strange feeling that maybe Boba Fett appeared in some weird thing before Episode 5, The Empire Strikes Back. But I'm just going to say Episode 5, Empire Strikes Back, because I don't count those other weird things.
So I'll go for the weird thing. I'll go for the Christmas special.
Anna, you're right. It is the Star Wars Holiday Special, which was, it's still, I don't know, you can't hardly see it anymore.
He was trying to talk me out of it. It's like, a Christmas special.
No, it's the Holiday Special.
Yeah, we go.
Star Wars Holiday Special was the first appearance of Boba Fett.
Yeah.
Excellent. Does anybody have any idea who he might have been based on? I just thought this was interesting. I would never have guessed it.
I have no idea.
It's a Sergio Leone guy.
Then no.
It's The Man with No Name. Clint Eastwood played the man with no name in one of those spaghetti westerns, and Boba Fett is based on him. All right. Hold on, though. I got some more. I said to you guys before we started taping this thing that the trivia was also going to be veriform.
You did, and we both looked at each other.
And you both were like, what the hell does that word? So what does that word mean? So
something to do with worms?
It does, yes. It means worm-like. Right? You have the only place I've ever heard that word actually come up is...
fishing?
No.
The Christmas special?
I do have many lures that are veriform, but... No, it's your appendix. It's called sometimes the veriform appendix because your appendix is a little worm-like thing.
Your appendix.
Your appendix is not worm-shaped? You get a weird one? Did you get yours removed?
So
let's just carry on.
So how is veriform related to Boba Fett?
Yeah, let's get.
How did Boba Fett? In the original Star Wars trilogy, Boba Fett kicks it.
Yes.
When he gets put into the Sarlacc.
Oh.
The Sarlacc pit.
The Sarlacc
I know
pit.
this. I remember this.
Yes.
I'm just going to take that as a win that I know what you're talking about.
Yeah. The Sarlacc is a big giant worm thing that lives under the thing. So then the question is, which one's bigger, a Sarlacc or a dune worm?
Dune worm.
What's a dune worm?
The series Dune.
The series Dune. Did you
know?
know?
Also,
Dune novels.
I've not seen that
in
either.
multiple adaptations.
No.
But the book is to be read.
Okay, I will put it on the list.
All right.
And interestingly, Dune was an inspiration for Star Wars, which was really quite obvious in retrospect. If you like seeing the most recent Dune movie, there you've got...
I've not seen... I want to see that, so no spoilers.
I'm not giving you spoilers.
Okay.
It's a galactic empire, okay, as in Star Wars, with an evil emperor and all sorts of space guns and spaceships and things like that, but everybody fights with swords.
Right.
Like the Jedi,
Yeah.
And an elite Imperial Guard, like the Stormtroopers and all that. Anyway.
Yep. So you're right.
I'm going with the dune worms.
It is the dune worm.
Yeah.
There's something like 400 meters is a dune worm,
huge.
and 100 meters is supposed to be what a sarlacc, because they're bigger by a factor of a few.
We don't actually see anything but the mouth of the sarlacc.
No, you don't. But of course, Star Wars nerds have gone off
decided
they've decided how
that
big
it's
it is.
100 meters long.
100 meters long. Okay, but that
We
leads
don't
to
even really know from
that
the
leads to
movie
the question.
that it's worm-like, that it's variform.
That's true, but it is.
See a mouth.
That leads to a random. I was just going down. Where I almost became a biologist because I think biology is also really, really cool. So then I was thinking about real worms, and I was asking myself, what is the largest real worm on Earth? So that's a two-part question. What is the largest earthworm? Like, this is the kind of worms you typically think of, like you'd fish with.
Something?
Well, how big?
How big?
If you get the species name, you got bonus extra points for weeks. But
what's the largest?
What's the length and maybe the weight or the weight of the largest earthworm?
3 meters.
3 meter earthworm.
That's just.
You can catch a huge fish on a 3 meter earthworm.
I don't know. 1 meter.
Yeah, you're right. It's 3 meters.
That's
just dead on. And this is the giant Gippsland earthworm. It's in Australia, of course, because everything terrifying.
So this is a subspecies or a set of earthworms that's that big. It's not like one freak mutant.
No, well, the average length of a thing in adult is about 1 meter, and they get up to about 3 meters at the biggest. And they weigh, they can weigh a few pounds. I mean, that's a whole earthworm.
Hey, what's the diameter of this thing?
An
inch.
Something.
He's holding up his fingers an inch.
I don't know. Something. But those are not the longest earthworms. What? The width?
Yeah.
No, I'm not making that up. I saw lots of pictures.
Okay.
Yep.
But they're not the longest worms. How long are the actual longest worms? They're not earthworms. They're different kinds. There's all kind of worms out there, of course.
Are they oceanic?
They're oceanic worms. And in fact, I think the biggest one ever was found washed up on a beach in England.
20 meters.
I'm supposed to be asking the trivia question. It's very uncomfortable.
How does it feel?
Yes, it's very uncomfortable.
Plucking
these
numbers
are
out of
hard,
thin
but
air.
she's still dominating.
Yeah. 19 meters.
Oh, come on.
Ooh, he goes for below. It's actually 55 meters.
Whoa.
50. There are these worms called bootlace worms that are, they're much thinner than the earthworms, so they weigh a lot less than.
Because they're suspended in water all the time, so they don't really.
They're these ribbon-like worms, but they can reach 55 meters long.
Oh, gosh.
That's an insanely long worm.
Like jellyfish kind of thing. Diaphanous.
This is why I don't go in the sea.
I don't think they're quite as
fragile.
Yeah, but they're very thin. Freaky.
Wow.
Freak me out. Anyway.
Wow. That's freaky trivia.
Sorry about that.
Yeah. My outro here was going to be about the Yarkovsky effect. Now I have a feeling it should be something like about worms, but
you can try.
Yeah.
But it would be completely made up.
Yeah. While it may have felt like measuring the length of the Earth's largest worm, it was just another episode of Walkabout the Galaxy. Give us 5 stars and we'll give you the universe. Be sure to follow us on Facebook and Instagram to get all our updates, and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel, Walkabout the Galaxy, where you can see the glitz and glamour of the Walkabout studio. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter
at walk_the_galaxy.
And ask us questions anywhere using hashtag AskWTG. Our theme music was composed by Richard Jerusik. Production assistance is provided by Logan Basinger. Thanks to our stamp collector listeners. Top is back. Stay safe. I'm Josh Caldwell.
I'm Hannah Sargent.
And I'm Jim Cooney.
We're the Astrocork, signing off until the next episode of Walkabout the Galaxy.
Another bog standard episode.